So if you look at yourself in a circus funhouse mirror, you look completely distorted. And the goal of the adaptive optics system is to introduce a second mirror that's the exact opposite shape and make you look flat again.
Buried deep inside the telescope, the deformable mirror changes shape up to 2,000 times a second to reverse the atmosphere's distortion.
And it has allowed us to take the sharpest images ever obtained of the center of the galaxy.
The sharpness of those images allows Gaz to make out individual stars near the center, a huge advance in astronomy. She begins recording their positions in 1995.
And every year since then, we've taken an image. Just take a picture.
Putting those annual snapshots together creates a time-lapse movie of stellar orbits. And what those movies reveal is astounding. The stars are whipping around the center of the Milky Way at phenomenal speeds.
These things are moving at several thousand, up to 10,000 kilometers per second, or 10 million miles per hour. They're really hauling.
To go that fast, the stars must be orbiting something extremely massive.
The mass that we infer is 4 million times the mass of the sun.
What could be 4 million times the mass of the sun, yet be completely invisible?
That is the proof of a black hole.
And not just any black hole, a supermassive, silent and sleeping, right in the center of our own galaxy.
In fact, this is the best evidence to date that we have for the existence of supermassive black holes, not only in the center of our own galaxy, but anywhere in the universe.
A supermassive black hole, 4 million times the mass of the sun, in the very center of our own Milky Way galaxy. From a cosmic perspective, it's right next door. And it raises a profound question. There are billions of galaxies out there. If ours has a supermassive black hole at its center, and if quasars are found at the centers of their galaxies, what about the others?
Are there black holes at the centers of galaxies? If they are, how common are they? We simply didn't know.
Could astronomers ever hope to find what lurks at the centers of other galaxies, millions of light years away, as Gez did in our Milky Way?
5, 4,
It would take another innovation in astronomy to make that possible.
and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, window on the universe.
When the Hubble Space Telescope starts delivering clear images of distant galaxies, a team of astronomers gets to work. They become known as the nukers because their focus is galactic nuclei, the centers of galaxies. One of them is Todd Lauer.
Step one, we take a picture of the galaxy with the Hubble Space Telescope. It shows us where the stars in the galaxy are, tells us its structure and exquisite resolution.
The key to finding supermassive black holes is to learn how fast the stars in the galaxy are moving. Galaxies outside our own are much too far away to measure the speed of individual stars. But by analyzing the way light is shifted from blue to red at different points in the galaxy, astronomers can put together an average speed of stars orbiting the center. It's accurate enough to create a replica in a computer.
The second step, where the real work begins, is to try to model the observations. And we actually do that by building models of galaxies in the computer.
It's known as Schwarzschild's method, developed by Princeton astronomer Martin Schwarzschild, son of Carl Schwarzschild, whose mathematics first described the possibility of black holes.
Martin Schwarzschild's trick was he would actually build up a model of the galaxy that not only had where the mass was, but also had how the stars were moving.
For each galaxy they investigate, the nukers painstakingly build a computer model, and then using trial and error, adjust the parameters of mass and velocity. trying to make the model match the original observations they got from the Hubble.
And we say, let's try a star here, let's try one over here, let's have it go around this way, let's have this one go around that way. And we do this thousands and thousands of times until we build up a library of how stars can orbit in this galaxy. Success is when observations of the model match the observations taken with the Hubble Space Telescope.
But that doesn't happen. The models are missing something.
We try it again and again and again, all with no black hole yet, and say, gee, we really can't get the observations explained by the model.
Only when they add an enormous invisible mass at the galaxy's center does the model match the Hubble observations.
Almost always, we have to put in a black hole at the center. We can't match the observations without a black hole in the model.
Of roughly 36 galaxies that the nukers investigate, virtually all of them require a supermassive black hole. And since then, other observations have made us even more certain that supermassives and galaxies go together.
Every galaxy we've looked for one, we have found a supermassive black hole in its center.
It's a stunning revelation. Supermassives, once an entirely unexpected category of black holes, may be common, not only at the center of our galaxy, but of all galaxies. Take galaxy M31, also known as the Great Andromeda Galaxy. It's 2.5 million light years away. On a clear night, you can see it from Earth. But even with the Hubble Space Telescope, we can't make out precise details of its center. Still, we're pretty sure there's something extremely massive hiding there. What if we could take a closer look? What if we could visit a galaxy far, far away? As we enter the outer part of Andromeda, we're still too far away to see what's lurking at the center. But we can make out a dense cluster of stars in the core, and that could be a sign that there's a giant black hole nearby. Billions of years ago, it would have been surrounded by gas and stars and other small black holes. The black hole may have powered a quasar, feeding madly and blasting out blinding radiation. Over hundreds of millions of years, it would have consumed all the available gas and the closest stars. These days, it's relatively quiet, but it has some distinctive features we've never seen before. First, it's colossal. If it were dropped in our solar system, Mercury, Venus, Earth, and Mars would all be trapped inside the event horizon. That's big, but it's nothing compared to the sheer mass, 100 million times the mass of the Sun. And the destruction won't end there. Jupiter won't last long. The gravitational field of the supermassive will grab hold and swallow it whole. Eventually, Saturn will suffer the same fate. The outer planets might survive, but in cold and dark orbits. This black hole rotates rapidly, distorting and dragging the fabric of space-time. Like all black holes, the event horizon is completely featureless. Remember, there's nothing there. It's just a boundary that conceals the interior. But the accretion disk can tell us a lot about what's going on. That's the fiery ring of gas and dust around the black hole. Imagine if we could release a swarm of autonomous robots to explore the accretion disk. The disk is spinning at an incredible speed, as much as half the speed of light. If Jupiter moved that fast, it would complete its entire orbit in a few hours. The region around the black hole is a cosmic tornado. Now our swarm is caught in the whirlwind too. They're like tracers, dropped into the storm to map the movement. The middle robot can send us images. It's following the leader like a race car speeding around the track. From here, the extreme warping of space-time around the black hole plays crazy tricks on our eyes. It looks like there's one accretion disk whipping around the equator and another arcing over and under the poles. But that's an illusion. The black hole's extreme gravity bends the path of light emitted behind the black hole and makes it look like the accretion disk is both above and below. There's actually nothing around the poles. It's just the passing light rays. That's gravitational lensing again. Drawing much closer to the event horizon, the gravitational lensing would become so extreme that one of my robots could look straight ahead and eventually see its own back, the light forever trapped in an eternal circle. So that's our tour of the supermassive black hole at the center of the Andromeda Galaxy. Pretty amazing. Also amazing, nothing in the mathematics led scientists to imagine that black holes could get that big. As strange as they are, ordinary stellar mass black holes were at least predicted by theory. Supermassives are a complete surprise.
For the stellar mass black holes, people thought about them from a theoretical perspective, and then we found them observationally. The supermassive black holes, the story has been inverted. We actually found evidence of them observationally first, and now we're working on the theory of how did these things come into being.
We already know that stars can collapse to create ordinary black holes, but supermassives are bigger by many orders of magnitude. Cygnus X1 is 15 times as big as our sun. The supermassive at the center of our Milky Way is 4 million times as big as our sun. The one in the Andromeda Galaxy is 100 million times as big as our sun. And it's not the biggest, not even close. There are supermassives 10, even 20 billion times the mass of our sun. How is it possible to make such gigantic black holes? Could supermassives have come from collapsed stars? That seems very unlikely. We don't know any stars billions of times bigger than the sun.
We know about black holes you might get from a dying star. They have several times the mass of the sun contained within them, but millions of times the mass of the sun. If that's the case, a dying star cannot have possibly made it.
So do these supermassives, millions or even billions of times heavier than the sun, somehow just grow, packing it on like voracious giants?
The wild thing about black holes is that they feed. They're constantly devouring anything that comes within their sphere of influence, so they grow.
But how exactly do they grow? What do they eat, and where do they find it?
We believe that black holes grow by accretion of gas. And the way this works is that you have a lot of gas around in the center of a galaxy, and this gas would then assemble and form an accretion disk.
The accretion disk is made up of hydrogen, helium, and other elements in a gaseous form. The immense gravity of the black hole pulls the gas in toward it. As it swirls around, it orbits closer and closer to the black hole, and the feeding begins.
The stuff in the inner regions would get slowly pulled in, sped up, will reach the event horizon, and then that's it.
Whatever gas crosses the event horizon disappears forever. the black hole has absorbed that material.
So it actually adds to the mass of the black hole.
So this is one way a black hole can grow, gradually nibbling gas and dust. But it's not the only way. Cygnus X1 has been slowly stripping material off a nearby star, a process that will likely go on for thousands or millions of years. But what if a black hole could rip an entire star apart in just a matter of years or even weeks? That would be a very violent event, and a team of space explorers is on the lookout.
Roger, copy.
This
Ready
is
for a
the
briefing?
Operations Control Center for a space telescope.
I have you 5x5, how many? We show beginning of track at 0330.
The Chandra X-ray Observatory.
Copy, machine data. Roger, please. 16 minutes, 1-6.
Orbiting up to 86,000 miles above the Earth, Chandra takes high-resolution images of objects that emit X-rays. This is one. A short-lived, extremely violent event called a transient, which fascinates James Guillochon.
Supernovae, the destruction of planets by their host stars. I'm just fascinated with destroying things for science.
James is investigating a mystery discovered by a colleague, Da-Sheng Lin. This blur on James's screen is actually a massive sudden burst of X-ray energy, caught by accident.
This little smudge popped up in the background of this image, and given its great distance, it's actually tremendously bright.
Could it be a black hole caught in the act of being born in the violent collapse of a huge star? A supernova. Perhaps. But the intense radiation released by supernova would only linger for a few months. So how long has this mystery object been blasting out X-rays? To find out, they look at images of that same part of the sky taken at earlier dates. 2015, 2011, 2008, 2005 July, 2005 April. No X-rays detected. But the X-rays are there just 3 months later in July. And the powerful, bright signal has continued for more than 10 years, from July 2005 to the present, far too long to be a supernova. So what could it be? A black hole that's not feeding is quiet and completely dark. It won't show up on any telescope. But a black hole that is feeding is different. When it feeds, it blasts out X-rays. So could this be a black hole that's suddenly begun devouring something big?
What effect will this have on anything that comes near? What would it do to a star that wanders too close? Well, it will flay a star, layer by layer, ultimately devouring the entire star.
Unlike Cygnus X1, this is no mere nibbling. This is a 10-year feeding frenzy. A massive black hole devouring an entire star in a cosmic blink of an eye. It's the result of a chance collision, when an unlucky star wanders too close and the black hole's extreme gravity actually rips it apart.
The gravity from the black hole will progressively get stronger and stronger as the star gets near. And at that point, the star will begin to deform.
It's called tidal disruption. It's similar to the way our moon's gravity easily moves all the world's oceans. The tides caused by a black hole would be billions of times stronger and much more violent.
You have these events where a star could be ripped apart by the black hole. So you would see sort of a plume of light from the last gasp of the material in the star.
But there is a chance for some part of the star to escape, as James illustrates.
As the star is elongated by the black hole's tidal forces, it will essentially be feeding the black hole at the same time as half of it is trying to escape. So everything above this point approximately will have the chance of leaving the galaxy. It's moving that rapidly. And everything below this point will fall back onto the black hole and eventually be consumed by it.
So this is another way for a black hole to gain weight. Unlike the slow, steady nibbling of Cygnus X1, this black hole is devouring most of an entire star in one gulp. But whether a black hole feeds suddenly by swallowing half a star or steadily through accretion, astronomers still face a problem when they try to understand how supermassives got so big: the timing problem. The trouble begins with the very oldest supermassives, quasars, those very bright, very distant, and ancient objects first discovered in the early 1960s.
The conundrum was when we started finding these quasars, very bright quasars, very early on in the universe.
They're giving off so much energy that they have to have very massive, supermassive black holes at their center.
But quasars are extremely far away, which means they're part of the very early universe, which began nearly 14 billion years ago.
Bright quasars, 600 million years after the Big Bang, a fraction of today's age.
And they're enormous.
So billion solar mass black holes, these behemoths, had to be in place when the universe was about 550 million years old.
Now you have a problem, because you have to grow something really big, really fast. And you are bumping up against sort of physical limits.
Whether a black hole is nibbling or gulping down its meal, it turns out that accretion, how black holes feed, has a speed limit. Named after English astronomer Arthur Eddington, the Eddington limit will not allow a black hole to feed too fast because of the light blasting out from its own accretion disk.
Light has a pressure. So photons can impart a force on something. We see this in winds from stars. Light is pushing out gas. So there's a limit to how fast you can feed a black hole before its own luminosity quenches its own growth.
So given the speed limit, how did early supermassives, quasars, get so big so fast? Could there be a way to bypass the speed limit entirely?
The problem is still time itself. How do you grow them to 1 billion times the mass of the sun? What are the conditions that you need for that kind of growth?
Some scientists are now asking, what if there's a way to create a black hole that's already much more massive from birth, giving it a head start?
If there was a physical mechanism that would allow you to make a black hole seed, which was much more massive from the get-go, then the timing crunch is not as much of an issue and the growing problem is not as acute.
The answer, some believe, is to create a black hole directly from a cloud of gas, a scenario called direct collapse. It starts with gas clouds made of hydrogen, helium, and other elements, the same raw materials from which stars are born.
The denser clouds will start to collapse under their own gravity. And as they collapse, parts that are more dense will collapse more quickly. And so what happens is the cloud fragments.
Those fragments continue collapsing until the hydrogen atoms within them begin to merge. Nuclear fusion begins and stars are created. But what if a giant gas cloud collapsed without making stars?
We realized that there are a set of physical conditions that would allow you to form a very large gas disk prior to the formation of any stars. So this gas disk starts getting unstable. That would allow the mass to sort of flow into the center very, very rapidly and make a very massive black hole.
It's something we've all seen in nature. From tornadoes to bathtubs, a vortex, but on a supermassive scale.
If you're in a bathtub and you pull the plug out and you see the water flowing in a vortex very fast down to the center, that's exactly what happens.
Direct collapse might be a way to create very large black holes early in the universe from enormous gas clouds, completely skipping the star stage. Because they would be so large already at birth, these direct collapse black holes would have a head start, helping them to quickly grow into the enormous young supermassives we see in the distant universe.
You could potentially have these direct collapse black holes. So black holes whose original masses, seed masses, the initial masses, are about 10,000 to maybe 100,000 times the mass of the sun, and that they form from the get-go with that mass.
Direct collapse may explain how enormous early supermassives got their start. But there's another fundamental question about supermassives. What is their role in the universe? Is their existence just a matter of chance? Or are they connected in some larger way to the very structure of the cosmos? Supermassive black holes don't exist in isolation. They seem to live in partnership with galaxies. Collections of millions, billions, or even trillions of stars bound together by gravity. Galaxies are the fundamental building blocks of our universe. So are the supermassive black holes at their centers somehow fundamental to their very existence?
We now just assume every galaxy, even ones we have yet to confirm, will have a supermassive black hole in their center.
It could be that instead of simply being oddities, that they are a key component to galaxies, a key component to the universe.
We've come in a very short time to realize that they likely inhabit the centers of all the galaxies. And that can really only happen if there's some symbiotic relationship between the evolution of a galaxy and the supermassive black hole in its core.
What could that relationship be? One intriguing clue relates to size.
The bigger the galaxy is, the more massive the black hole appears to be. So these black holes at the center seem to know about their larger scale environment.
So which comes first, the galaxy or the supermassive black hole? It's not that simple. It appears they somehow grow in tandem.
It's hard for one to form first and affect the other. So today, we think that whatever formed one had to form the other as a byproduct of that process, and that there has to be some feedback mechanism between the black hole and the galaxy that keeps the growth of the two in lock sync.
The way galaxies grow is by forming new stars from clouds of hydrogen gas.
Gas is essentially the fuel for star formation, just like gas is the fuel for our cars. And so if you run out of gas, you run out of new stars.
So are supermassive black holes somehow interfering with star formation?
When a black hole is growing, a tremendous amount of energy is being liberated and sent out into the galaxy. And so we think that some of that energy goes to warm up gas. And gas that's too warm will not form stars anymore.
The heat produced by a growing black hole makes it impossible for stars to form nearby.
And so one way that a growing black hole can influence its host galaxy is by quenching the star formation.
In effect, the growth of the supermassive determines whether or not its host galaxy grows or stagnates.
They have a kind of eating phase and then a quiescent phase. So they seem to be involved with the formation of the galaxy in that way, and then stabilizing of the galaxy at the same time.
So these mysterious supermassives may actually control the building of the universe. Not so much by their size, but by the way the energy they generate shapes galaxies.
By mass, if you count up all the black holes in the universe, the tiny ones as well as the supermassive ones, the ultramassive ones, black holes are nothing. However, energetically, how much power the galaxy gets and at what time as it assembles seems to be dictated by the central black hole. So they might well be the key players in the universe.
In the next 2 years, NASA plans to launch the James Webb Space Telescope. Humanity's most powerful telescope ever, the James Webb is designed to look in the infrared, allowing it to see farther back in time than Hubble, getting a look at the first stars and galaxies that formed after the Big Bang. Hopes are high that the James Webb Space Telescope will help solve many of the remaining mysteries about the earliest supermassive black holes.
The James Webb Space Telescope is tuned specifically to observe the early universe when galaxies were being born. That could give us deeper understanding of how you end up with a supermassive black hole in your galaxy to begin with.
Technology is moving really fast, and as a result, we have really fundamental new views of the universe. I think we are really living in a golden era of astronomy.
And the James Webb Space Telescope isn't the only new development that promises to solve some of the mysteries around black holes.
I believe have infrared components.
A group of scientists led by Shep Doleman is now attempting the impossible: to take a picture of a black hole.
It's interesting that we can say something about the accretion flow near the black hole at all.
And if some of this linear behavior survives, maybe we'll have a way of interpreting it.
The project is called the Event Horizon Telescope.
So it depends on when those...
The basic goal of the Event Horizon Telescope is really to see the unseeable. It's to bring into focus something that science has told us for many, many years is precisely something we can't observe, the black hole.
Their primary target is Sagittarius A star, the supermassive in the center of our Milky Way galaxy. They're using a global network of radio telescopes.
We need good weather at 8 different telescopes all around the world, and that is a tall order.
But if black holes are invisible, what exactly do they hope to photograph?
What we're trying to photograph really is the shadow. So as this gas around the black hole swirls inwards and actually hits the event horizon, it leaves a silhouette, a very well-defined shadow on the surrounding light. So really it should look like a donut with its very well-defined hole. And that's the picture that we are after.
If I convert that into frequencies, I get a 2 pi square there.
The team has conducted their first observing run and is processing the data now.
And you're saying the velocity...
It's hoped that these new technologies will give us an unprecedented view of black holes in our universe. But there is one new technology that is already delivering results. And that brings us back here to LIGO, a key player in the black hole drama, to an idea that took root way ahead of its time: gravitational waves. With general relativity, his theory of gravity, Einstein predicts that when an object moves, it can create ripples in space and time, an actual squeezing and stretching of space itself. One of the holy grails of 20th century physics was to detect these gravitational waves.
That was not easy to do with general relativity because all the effects that you could think of were infinitesimally small, very, very difficult to measure.
The thinking was, if gravitational waves could be measured, it would confirm Einstein's prediction. And there could be an added benefit. It might also prove the existence of black holes and help solve the mystery of how supermassives grow. But how to detect gravitational waves? In 1970, the problem caught the attention of a young experimental physicist, Ray Weiss. Ray had the perfect background to hunt for gravitational waves. For decades, he'd been working with more familiar waves, sound waves.
We were immigrants, we were German Jews, and a lot of our friends were very, very interested in music.
Ray devoted himself to coaxing every subtle nuance he could out of recorded music.
Those records had a terrible problem. When the music was loud, it sounded wonderful. When the music was real quiet and slow, what you heard was this shh, like that, a hissing noise. And that was so annoying.
The lessons he learns trying to eliminate noise in recordings will pay off later when Ray turns his attention to detecting gravitational waves.
You have to understand how a gravitational wave does its dirty work.
As a physics problem, gravitational waves are not unlike sound waves.
Suppose the wave comes from something that is in some way moving and oscillating.
A sound wave compresses and expands air. A gravitational wave compresses and expands space and everything in it.
If a wave came through the Earth, it would cause space to expand momentarily and then contract again. It keeps doing it. It's a thing that goes blip, 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 right along like that.
So how to measure the extremely tiny expansion and contraction of space? Ray's idea was to use light. Send a beam of light from one place to another and measure the time it takes to get there. That's how the exact distance to the moon was calculated, bouncing a laser beam from the Earth off a mirror left behind by Apollo 11 astronauts. From the duration of the round trip, scientists could determine the distance. Ray came up with an ingenious design for an instrument that uses lasers and mirrors to detect the faint expansions and contractions of space that would be caused by a gravitational wave. It's called a laser interferometer. It works by firing a laser into a splitter. Half of the light continues straight ahead towards one mirror, while the other half is sent towards another mirror. The distant mirrors bounce the light beams back, where they rejoin at a photodetector. If the distances the two beams travel are exactly the same, the system is designed so the two beams cancel each other out. The detector sees nothing.
You set the trap to measure the gravitational wave. Now comes a gravitational wave that's coming, let's say, at this structure.
If a gravitational wave passes through, it briefly changes the length of the arms. The light beams no longer arrive back at the same time to cancel each other out. A gravitational wave hits, light appears at the detector. The trap has sprung.
That's the basic idea. It's a very straightforward measurement.
A clever idea and simple in principle. But the devil and the Nobel Prize lie in the details. The difference in length between the two arms would be tiny beyond imagining.
How tiny? We'll take the size of an atom. It's less than that. Go down by a factor of 100,000. That's the nucleus of an atom. It's less than that. It was 100 times below that. So we're talking about really itsy bitsy teeny weeny. I thought it was crazy. I think everybody's initial reaction to the idea was, this is going to be impossible.
In 1973, Kip Thorne puts his skepticism on the record in a classic textbook, doubting it will ever work. But Kip has never heard Ray Weiss explain his plan in detail. And when he does...
We spent the whole night talking. And so I said, no, it's very possible. And within no time at all, 20 minutes, maybe half an hour, Kip was solidly understanding this thing. And he says, yep.
And I ate crow the rest of my career because once I had talked with Ray about it in detail, I decided I would spend a large fraction of the rest of my career helping the experimenters.
But it will take 40 years and enormous sums of money to bring Ray and Kip's vision to reality.
Getting LIGO funded was extremely controversial. Hundreds of millions of dollars to detect a signal that had never been seen before. There were many people who feared that LIGO would suck the money out of the room. And so there was a lot of controversy. What everybody could agree on was this was extremely difficult.
With such a sensitive instrument, one of the biggest challenges is Ray Weiss's old hi-fi nemesis, noise.
Ground motion, the seismic motion of the Earth, acoustics noise, sounds, everything would tend to move that mirror.
Turns out, even the emptiness of a total vacuum creates a potentially crippling problem. At subatomic distances, the weird randomness of the quantum world causes a ruckus in the mirrors.
This quantum noise is due to quantum fluctuations. These mirrors are doing what an electron does inside an atom. They're jiggling around.
Exquisite sensitivity, extreme vacuum, hundreds of thousands of electronic circuits. LIGO is one of the most complex instruments in the history of science. And as a final means of eliminating false signals, they build not one, but two complete installations. One in Washington State and another in Louisiana.
And so the LIGO designers did it right. They designed more than one detector, separated from one another by great distances, so that if you detect something in one and not in the other, then, go back and check your electronics. Check to see if it was April Fool's Day and somebody didn't just tweak the knobs.
Early fall 2015. Both locations are operating, but the first official science run has not yet begun. They're still testing. In the early hours of Sunday, September 14th, 2015, a scientist in Louisiana makes a fateful decision.
The one up on
Robert Schofield has been working all weekend, doing final calibrations.
Alrighty, let's take a spectrum.
He has one last test.
So let's see where this computer is getting its power.
But it's late, and the equipment is not cooperating.
It was about 4 or so in the morning, and we still had about another hour of work to do. And we were like, yeah, things aren't working so well, and I'm really tired. Let's not do this last hour or so of work.
They call it a night, and 40 minutes later, in the silence of their inactivity, they open the door to history. A powerful gravitational wave rumbles through both detectors, Louisiana and Washington. Had Robert Schofield worked 40 more minutes that night with the instruments in test mode, a signal that had been on its way for 1.3 billion years would never have been recorded.
I like to say, one of my biggest contributions to LIGO has been my laziness that day.
I got an email from somebody here saying, hey, you look at this place on the web. I looked at that, and I said, holy.
It was so strong that you could see it by eye in the data. It was too good to be true.
But it was true. In fact, it was loud and surprisingly clear.
And it just sang at you. There was, standing out.
The signal lasted less than a second. But in that briefest of moments, it delivered a cosmically profound message more than 1 billion years in the making, proving the existence of black holes.
So what we saw in the signal involved oscillations of the mirrors that were slow at first, became faster and faster and faster. And this was precisely the kind of behavior that you would expect from gravitational waves caused by two black holes going around each other, spiraling together.
Two massive black holes, one 29 times the mass of the sun, the other 36 times the mass of the sun, whipping around each other hundreds of times a second, finally completing their act of mutual destruction by merging, creating a single, larger black hole of 62 solar masses. The violent merger converts some of the mass into an apocalyptic release of energy beyond anything ever before witnessed.
The collision, in effect, creates a veritable storm in the fabric or the shape of space and time. As though you had taken 3 suns, you had annihilated them completely, converted it into gravitational waves. The power was 50 times higher than the output power of all the stars in the universe put together, in a fraction of a second. But the most powerful explosion that humans have ever had any evidence for, with the exception of the Big Bang.
Since that very first signal in September 2015, LIGO has detected several more collisions of black holes. In October 2017, Ray Weiss, Kip Thorne, and LIGO's former director Barry Barish received the Nobel Prize. The LIGO discoveries prove that black holes can merge. One way they can grow bigger quickly.
More and more evidence of these merging black holes tells us there are a lot of these stellar black holes around that they can find each other and merge.
And the discovery opened an entirely new way of observing the universe.
We've always thought of astronomy as an observational field where we are looking at radiation. We are seeing things. But this is not radiation. This is something much more fundamental. These are sort of fundamental tremors in space-time itself. We can now hear the universe.
For the first time, astronomers have simultaneously seen and heard a cosmic event. In August 2017, LIGO detected gravitational waves from a collision of 2 neutron stars. Black holes are empty space, but neutron stars are dense, dead stars that can crash together and light up the skies. When telescopes and satellites around the globe pointed in the direction of the sound, the world saw fireworks in an explosive collision and afterglow. Possibly, the collision resulted in the creation of a new black hole. But unless we observe the formation of a black hole, there is much we will never know. Because so much about black holes is irretrievably out of our reach, we can never know where they came from, what's inside, or their history. but we can imagine their future. The number of black holes in the universe is increasing, and they're getting bigger. Stars collapse, black holes feed and merge, new ones form. Could it be that one day everything will end up inside them and they will rule the universe? Untold trillions upon trillions of years after this happens, and the last bits of matter cross their event horizons, black holes themselves may radiate away and vanish from this reality. Their mysteries are many, and we're just starting to unlock the secrets of these strange, powerful places. But one thing is certain: black holes will continue to intrigue us, tantalize us, and challenge both our science and our imaginations.